All right then. Well, a few more things about tensors. And so I want to finish up this mathematics today and then move on to liquid crystal physics on Friday. So when we were talking about math on Monday, right, and we talked about pseudo tensors versus proper tensors. Uh, Proper tensors. And the same things go for pseudo vectors versus proper vectors. And pseudo scalars versus proper scalars. Right? And the way I presented it to you in that class on Monday had to do with whether or not the sign of an object, positive or negative sign of an object, depends on convention, right? That whether or not it depends on the choice of the right-hand rule versus the left-hand rule. And so for these pseudo objects, we could say there's a plus or minus sign that depends on right hand versus left hand rule. And here, the sign does not depend on the right hand versus the left hand rule. So this is a nice way to distinguish between those things. And it means that when you're looking at a mathematical description, you could say that the objects in this column have an odd number of epsilons, and the objects in this column have an even number of epsilons. Or you could say, if you're writing it as cross products of vectors, instead of writing it with epsilons, you could say this has an odd number of cross products. Versus an even number of cross products. And of course, 0 is an even number, right? So something that has no cross products, cross products.
Question.
It has no cross products counts as even. Chris, question.
Does it matter how the cross products are manipulated in an equation? So say you have two cross products that are added together, like a cross product plus a cross product, versus like the vector triple product of A cross B cross C. Does that, so if you have two cross products in addition versus two cross products in multiplication, are they still both proper vectors? Or
okay,
case,
so
both cases?
the first thing that you're saying is like A cross B plus C cross D, right? And then you're comparing that with, for example, A cross B dot C cross D, right?
Yes, or a singular one like C cross A cross B. No dot product, just C cross A cross B cross C. Do you know what I'm saying?
A cross B cross C.
Yeah, that was what I meant for my other one.
Sure. All right. Well, let's think about each of these, right? So first, I have to say explicitly, let's assume A, B C, D are proper vectors. Okay, they don't already have any cross products built into them, right? And so we're assuming that these are things like position or velocity or momentum, right, which are proper vectors. Okay, and in that case, A cross B, the cross product of two proper vectors, that's a pseudovector. C cross D is also a pseudovector. And so you have the sum here of pseudovectors, which is also a pseudovector. Okay. In the example down here, this one that you were just speaking of, B cross C is a pseudovector. So when we look at the whole combination, right, this is proper cross pseudo. And so there is, if you switch the right-hand rule to the left-hand rule, you have one sign change there and another sign change with that, right? And so those two sign changes cancel, and the combination of those things is then a proper vector.
Okay, so when you say, so then for future reference, then when you say the power of how many cross products, you mean like in the fashion that we have that bottom example, where they're actually like piled together and not through any addition or subtraction.
Correct.
Okay, I just wanted
Within
to
a
make sure.
single term with no addition or subtraction. Yes, excellent point, Chris.
Thank you.
Yes, so this is two piled together in one term, right? Whereas up here, it's one in this term, so this is pseudo, and one in this term, so this is pseudo. And when you add things instead of multiplying, you have to be adding the same kind of object. So when I'm counting, that's counting term by term. Okay. And likewise in here, this is all one term, right? Everything is multiplied, not added there. Right. So that is also proper, right? In this case, it's a proper scalar. Okay, very good. There is an alternative way to say the same thing, okay? And it's an alternative way that I want to mention to you because you might see it in the literature, even though it's not my favorite way to say it. Okay, so my favorite way has to do with checking whether things depend on this choice of convention or not, okay? The alternative way is to say, what happens under an inversion? So an inversion means a transformation of coordinates where x goes to negative x and y goes to negative y and z goes to negative z. So it's taking your coordinate system and flipping it inside out, right? And so, the original coordinate system like this is x, y, z, and then the new coordinate system is going to be x prime is negative x, and y prime is negative y, and z prime is negative z. So you could say, what happens to a scalar if you make this change of coordinates, right? And the answer is a scalar remains unchanged because it's a scalar. It remains unchanged. It is a pure number by itself. And so if we have a pure number like the mass of a particle, that does not change when you do a change of coordinates like this, okay? So a scalar, I'll call it, it's a proper scalar, okay? How about a proper vector, like velocity? So if you have a velocity vector, if something is moving, I'll just draw a vector here. Here's a velocity for a particle, okay? So this velocity has an x component and a y component and a z component. Now, if we change to the x prime, y prime, z prime coordinates, then the components of the velocity all change sign. Okay, red. The components change sign. That is, the new x prime component of velocity is the negative of the old x component of velocity. Same for y, same for z. So what about a proper tensor? Well, it depends on the rank of the tensor. What about a tensor of rank 2? Okay, so if we have a Tij, for example, if we switch x, y, and z to x prime, y prime, z prime, then if we look at the xx component of Tij, right, and now we do this flip of sign, right, the xx component changes to an x prime component, right, which has two sign changes from the original thing. So those two sign changes cancel each other. So the components will be unchanged. Okay. In general, if you have anything with an even rank, the components do not change. And if you have something with an odd rank, the components change sign. Okay, so this is for proper expressions. Okay. What about for pseudo expressions? A pseudo scalar or a pseudo vector or a pseudo tensor? Well, for any of these kinds of expressions, they do the opposite of what a proper expression would do for the same rank. And so a pseudo scalar will change sign. A pseudo vector will remain unchanged. And a pseudo tensor of rank 2 will change sign. So it does the opposite of what a proper expression ought to do. Okay. So this is a way of thinking about the distinction between proper and pseudo in terms of the inversion transformation, as opposed to thinking about it in terms of right-hand rule versus left-hand rule. It's not my favorite way of thinking about it, but it's a respectable alternative. And so you'll hear people talking about this kind of thing also. Now, one way in which this is especially important is there's, you could ask, what happens under a reflection? That is a mirror image. Okay. This is a different kind of transformation, right? So suppose we have a mirror here. And so here we see some physical system, like there's a mass moving with some velocity. Okay. Then if we look in the mirror, it looks like the mass is moving with a velocity like that. Okay. So the mirror is changing the x component of the velocity, but it's not changing the y or z components. So if I label x, y, z, then when we reflect in this mirror, right? So here's a mirror in the YZ plane, perpendicular to X. Right? And this mirror does a reflection where we could say X goes to negative X, but Y stays the same and Z stays the same. So it's a little bit different from the inversion, right? With the inversion, all three of the coordinates are changing sign. With the reflection, only one of them is changing and the other two are staying the same. We could compare that with a 180-degree rotation. Okay? If you have a 180-degree rotation, well, you have to say, of course, what axis you're rotating about. What if you're rotating about the x-axis? Okay? So if you're rotating about the x-axis, so X, Y, Z, okay? And we're gonna rotate about the x-axis by 180 degrees so that Z gets rotated down there to negative Z and Y gets rotated over there to negative Y, okay? So that after the rotation, after the rotation, X stays the same and Y changes to negative Y. So Y prime is negative Y. And Z prime is negative Z. Okay. So under the rotation, we have X goes to X and Y goes to negative Y and Z goes to negative Z. So you could say that the rotation, this rotation combined with this reflection equals the inversion, right? Because the rotation changes two of the coordinates The reflection changes one coordinate. And so if you do both of those things, you get the inversion. Okay? So we could write that as a combination of operations, right? We could say that the inversion equals a rotation of 180 degrees about the x-axis, combined with a reflection in the YZ plane.
I get
Or
these two operators are changeable. The order of these two operators is changeable, right?
yes, these two operators could go in either sequence. I could do the rotation first or the reflection first. Correct. And I could also say, likewise, that the reflection in the YZ plane is equal to the rotation of 180 degrees about x combined with the inversion. The inversion changes the sign of all three coordinates, and then this rotation changes two of them back. And then you only have one change over there. So if you want to know what does a reflection do to some object, you have to think about it as what is an inversion due to the object and what is the rotation due to the object. And if you combine those two things, you can put together what happens to any object under a reflection. Okay. So let me just show you one quick example of that, because this is something that I was so confused about when I was a student. Okay, so suppose we go back to this mirror image thing. Okay, so here's our mirror. Okay, and over here we have a record player. Okay, so it is spinning a disc of vinyl over there. So it spins around in this direction. Okay, so the vinyl disc is in the XY plane. All right, so here's X, Y, Z. Okay, the vinyl disc is in the XY plane, and there's angular momentum, right, for the disc that's spinning. Right? So the angular momentum has a direction given by the right-hand rule. So the angular momentum, L, is pointing upwards. Okay? Now, if we look at it in the mirror, what do we see? Okay? So over here in the mirror, we see the record that's turning in the opposite direction. And it has angular momentum. And because it's spinning in the opposite direction, it has angular momentum like that. Okay. And now you might look at this and say, wait a minute, there's something wrong here, right, that this angular momentum vector, where am I? This angular momentum vector doesn't look like the reflection of that angular momentum vector, right? Whereas, if you see there's, I don't know, a bug on the record, right? So here's a little bug, right? And it has a velocity like this. And over here, here's the bug. And it has a velocity like that. So the velocity vector looks like a mirror image, right? But the angular momentum vector doesn't look like it's a mirror image. The angular momentum vector looks like it's doing something the opposite of what it ought to be doing, right? And so when I was a student, I thought I had discovered a fundamental flaw in the laws of physics, but actually I had not, right? It just is the point that the velocity is a proper vector and the angular momentum is a pseudo vector, right? And so pseudo vectors will do the opposite thing from proper vectors under inversions. And here the mirror is oriented in the right way so that a reflection does the same thing as an inversion to the angular momentum. Okay, so that is a story about distinguishing proper mathematical expressions from pseudo mathematical expressions. And they are both totally reasonable things to work with. You just have to be careful about how you combine them and to combine them so that you understand how your final expression is going to change, either if you make a choice of convention, right-hand rule versus left-hand rule, or a choice of flipping the coordinates with an inversion or rotation. Okay, any questions about these kinds of things? Okay. I hope this alternative view about inversions and rotations and reflections makes things clearer rather than more confusing, right? I mean, I introduced this subject by talking about right-hand rule versus left-hand rule, because for me, that seems so easy compared to the other way of doing it. And maybe you agree with me, maybe you don't. You certainly need to be aware of the other way of looking at things with inversions or reflections, because that's what most people other than me talk about. And so that's what you would see mostly in the literature. Okay. For the last topic related to tensors, I want to talk about visualizing tensors. This is something that came up in the last class. There was one example that I was asked about. And it comes up a lot because this is one aspect of tensors that students are sometimes uncomfortable with. Right? I have a feeling that there are a lot of students who like vectors because they think, oh, vectors, they're like arrows, right? Like an Apple Pencil. And so they have some magnitude and direction in space. And we know just what we're looking at when we have a vector. All right. And we get to represent it in terms of magnitude and direction, or we get to represent it in terms of the X and Y and Z components. And those are two sort of equivalent ways to think about vectors, and you can go back and forth between them. The question then is, what's the analogous thing with tensors, right? That we know about tensor components. So if we have a rank 2 tensor that has 9 components. Okay? So it's a set of 9 numbers, the same way that a vector could be described by a set of 3 numbers. Okay? But for a vector, we know we can translate that into a magnitude and a direction. Okay? And then visualize it in 3D space. Okay, so then we can say, what's the equivalent thing for tensors? We want to know, how does the set of 9 numbers correspond to a set of magnitudes, plural, and directions, plural? It is possible to do that. Okay, so let me tell you what I can about how to do that correspondence. First of all, let me say that for any tensor, and I'm going to say any tensor of rank 2, that is a 3 by 3 matrix, so a tensor Tij. Okay, we can break it into symmetric and anti-symmetric parts. So to make sure you know these terms, if you think about a matrix, right, a matrix is symmetric if the things in the northeast corner equal things in the southwest corner. Okay, so that is symmetric under flipping about this diagonal. So, for example, we could have a tensor like 1, 2, 3, 4, 5, 6, 4, 5, 6. That's symmetric. That means we have Sij equals Sji. Okay, so the thing that's in row I, column J, equals the number that's in row J, column I. That is symmetric. By comparison, an anti-symmetric matrix or tensor is one where if you flip about this axis, you get the opposite sign. Right? So if you have 4, 5, 6, you need to have -4, -5, -6. Necessarily, that means that whatever is on the diagonal has to be 0. Right? It has to be 0 so that, when you flip this about this diagonal, it stays in the same position, right? So it has to be equal to its own negative, right? And 0 is the only number like that that's equal to its own negative. Okay. So Aij equals negative Aji. Now, what if you have any old tensor that is neither symmetric nor anti-symmetric? Some tensor Tij that's neither of those things. Well, the claim is you can break it into a symmetric piece plus an anti-symmetric piece. Okay? And this is actually not difficult. Okay? The symmetric piece is Tij plus Tji over 2, and the anti-symmetric piece is Tij minus Tji over 2. And then if you add those two things together, the Tij pieces, they add up, right? You have a half Tij plus a half Tij. That makes Tij. And the Tji pieces, they cancel. So you just get Tij. So to show you an example, okay, for an example, if I come up with some random tensor that is neither symmetric nor anti-symmetric, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's neither symmetric nor anti-symmetric. This is Tij. Well, then Sij is going to be the average for each piece of what's there plus the transpose. Okay, so 1, 2, 3 on the diagonal, and then let's see, for this this position right there, I want the average of 4 and 11. What's that? 5.5. And for the corner, I want the average of 5 and 8. What's that? 6.5. And then here, 7.5, 7.5. And then for the anti-symmetric guy, I want the half the difference. So 0, 0, 0 on the diagonal, and then 1.5 minus 1.5. And here, 1.5 minus 1.5. And 1.5 minus 1.5. I hope I got this right. This wasn't in my notes, but hopefully I did this right. And these two matrices over here add up to that thing, right? Okay. I didn't embarrass myself, did I? Okay, good. All right, so you can do this with any input tensor. Okay, so why am I doing this? Well, it's because I can think of a way to visualize a symmetric thing, and I can think of a way to visualize an anti-symmetric thing. And so I'm going to tell you, whatever tensor you start with, step one, break it into a symmetric and an anti-symmetric parts. And then I'll tell you how to visualize each of those things separately. Okay, let's do the anti-symmetric. Okay, so if I want to visualize the anti-symmetric part, okay, so I have an anti-symmetric tensor, Aij. The point is that this anti-symmetric tensor can be mapped onto a pseudovector. That is, I can define a pseudovector Pk as epsilon ijk aij. All right. So here you can see that the right-hand side of this equation is anti-symmetric between I and j. The left, well, this piece is, and this piece is also. So, you know, these things don't cancel. You get a non-zero vector that way. So let's say for the example that I made up on the spur of the moment, this thing with the 1.5s and negative 1.5s. Okay, 1.5, 1.5, 1.5, 0, 0, 0, negative 1.5, negative 1.5. Okay, let's do this transformation and see what is the P vector. Okay. So P sub X is epsilon X, Y, Z. No, almost. Let's try that again. It's epsilon Y, Z, X, A, Y, Z plus epsilon Z, Y, X, A, Z, Y. Okay. Those are the only two terms that are not zero, and then plus a lot of zeros. Okay, epsilon Y, Z, X is 1. A, Y, Z. Okay, what's that? Negative 1.5. Row, that's row Y column Z, negative 1.5. Plus epsilon Z, Y, X. That's negative 1. A, Z, Y. The row Z, column Y. That is 1.5. Okay. This is a number. It is negative 3. Okay. Similarly, if you do the other things, PY and PZ are negative 3. Okay. So this A maps onto a vector P, which is negative 3, negative 3, negative 3. You know how to visualize that, right? It is a vector with a magnitude of 3 root 3 and a direction in the negative, negative, negative diagonal. Similarly, you can go back from the pseudo vector to the A, right? And the antisymmetric tensor could be written as Aij equals 1/2 epsilon ijk pk. Okay? And so that means, for example, A x y is 1/2 epsilon x y z p z. So that's 1/2 times 1 epsilon x y z. And pz is negative 3. So that is negative 1.5. And so that's row X, column Y. That's right there, negative 1.5. Okay, so by using this rule to go from an antisymmetric matrix to a pseudo vector and vice versa, you can take the antisymmetric matrix, transform it into a pseudo vector, and visualize that. And so physically, what you might say is an antisymmetric matrix corresponds to a circulation in a certain plane, like a current loop moving around in a certain plane. And then you're transforming that into a pseudo vector using the right-hand rule to say what's happening in this plane corresponds to a vector sticking perpendicular to that plane with a sign represented by the right-hand rule. So the antisymmetric matrix or tensor, that's a circulation. So there's a special plane associated with it, and that corresponds to the pseudo vector normal to the plane, perpendicular to the plane. Okay,
Excuse me.
please.
Can I say that this anti-symmetric part has 3 degrees of freedoms?
Yes, you can indeed say that. That would be a fine thing to say. Yes, you could say that the original tensor here has 9 degrees of freedom. Okay, and then we're breaking it up like this. Okay, so for the symmetric part, how many degrees of freedom are there? Well, it's 1, 2, 3 on the diagonal, and then 4, 5, 6 off the diagonal, and then these guys are locked in to to 4, 5, and 6. Right? So this symmetric has 6 degrees of freedom. The anti-symmetric one has 1, 2, 3 degrees of freedom. These guys have to be 0. These guys are locked into those guys. Right? So this has, 3 degrees of freedom. And of course, 6 plus 3 equals 9, right? So we've accounted for everything. Okay? So when we are making the correspondence between the anti-symmetric matrix and a pseudo-vector, right? It's a pseudo-vector in 3-dimensional space. So it also has 3 degrees of freedom, right? So we're taking one thing with 3 degrees of freedom and transforming it into a different thing with 3 degrees of freedom. So that's good, right? That keeps everything balanced. And then we're visualizing the pseudo vector with the 3 degrees of freedom.
Okay.
Okay, excellent. Now, what about the symmetric part? Okay, so for the symmetric part, okay, if we want to visualize the symmetric part, well, we know that has 6 degrees of freedom. Okay. The way to visualize that is to calculate the eigenvalues and eigenvectors. Okay. So hopefully you guys are familiar with this concept of eigenvalues and eigenvectors from your preceding linear algebra classes. Okay, so you know that if you have a real symmetric matrix, it has real eigenvalues. It has 3 real eigenvalues. Well, they might be the same as each other. They might be different from each other. We don't know if they're the same or different, but there are 3 numbers which are the eigenvalues of that matrix. Each of those eigenvalues corresponds to an eigenvector. Right? There are 3 eigenvectors which can be defined as unit vectors and they are perpendicular to each other. The point that I'm getting towards is that these three eigenvalues, these are the magnitudes associated with the tensor Sij, the symmetric part of the tensor. So there are three magnitudes, right? It's not like a vector that has one magnitude. There are three magnitudes here. And the eigenvectors are the directions associated with the tensor, the symmetric part of the tensor. Right? Let's count to see if this is the right number of degrees of freedom. Right? If I want to know, if I want to define the first unit vector of the three, right? Well, that takes two angles to define it, right? Because there is a angle down from the z-axis and then another angle going around, okay? So it takes two angles to specify what is the unit, the first unit vector, okay? Now I want a second unit vector, which is perpendicular to the first one, okay? So the second unit vector must be somewhere in this plane perpendicular to the first one. That takes one angle to specify. Then the third unit vector has to be perpendicular to the first two. So it's locked in to the first two. So it doesn't need any angles to define. Okay. So we need three numbers, three angles to define these three eigenvectors that are mutually perpendicular unit vectors. So this is 3 degrees of freedom. This is another 3 degrees of freedom. So together they make 6, and that's the 6 that we were looking for up there. How am I doing on time? Okay, let me just take a couple of minutes to briefly show you about how you might visualize those things in a picture. Okay, so I'm going to switch to Mathematica just for a couple minutes here, and then I'll be done. All right, so if I stop this sharing, and I'll make another Mathematica share. Share Mathematica. Here is a Mathematica notebook I made, okay, which starts by making a tensor with random numbers. Here's a tensor with random numbers, okay? Then I break it into a symmetric tensor and an anti-symmetric tensor, right? Just the same way I did in my head before, okay? So this is the symmetric one. This is the anti-symmetric one. So hopefully you can see that the S and A add up to the original tensor T. And hopefully you can see that A is anti-symmetric and S is symmetric. Okay, now I want to visualize the symmetric tensor and the anti-symmetric tensor. The antisymmetric one, that's just going to be an arrow, right? So I take the antisymmetric one, I change it into a pseudo vector, then I draw an arrow to represent that pseudo vector. Okay. For the symmetric one, I want to represent that by an ellipsoid. That is an object that is stretched out. It's like a sphere that gets stretched out by 3 different amounts in 3 different orientations. So here you can say this is an ellipsoid that is stretched out a lot this way and a medium amount this way, and it's really narrow this way. All right. So a good way to represent the 3 eigenvalues and 3 eigenvectors is to let the eigenvectors define the 3 axes of the ellipsoid, right? The 3 axes where the ellipsoid gets stretched different amounts. And then the eigenvectors say, how much is it stretched along each of those 3 axes? Now, there is one thing that makes this exercise a little bit annoying, okay? That point is, what if the eigenvalues are negative? Okay. The eigenvalues could be negative, right? The eigenvalues are guaranteed to be real, but they might be negative. So what do I do? All right. Well, one answer to that is I could just add something to all the eigenvalues to sort of offset them, to push them up to be positive, right? So then I have to like keep track of how much did I do the offset. And that's a spherically symmetric thing. So here I just made a little sphere with a number in it, and that represents, you know, what's the average of the eigenvalues? How much did I have to offset them to make them positive? The point is that my tensor visualization then comes down to really 3 objects, right? It comes down to an arrow for the pseudovector and a sphere for whatever is this offset amount, and then the ellipsoid that has to do with what are the 3 special directions, the eigenvectors, and the 3 magnitudes of how much are things stretched in each of those 3 directions. So here is some Mathematica code that I made, which generates a lot of random examples. I'll just run it again and it'll make another random example. Poof, there's another random example, okay? And so here is a tensor, and this ellipsoid came out looking like an American football, right? That it's approximately uniaxial. So just stretched in one direction and approximately the same in the other 2. That was just random. I also have an alternative version of the code where down here, you can use these sliders to set the 9 components of the tensor and see how each of those changes both the ellipsoid and the arrow for the antisymmetric part. So I'm going to post that on the Blackboard site for this class, and you can download it and practice with that. And by all means, if you have questions after you practice, we can talk about that. I'm going to say one more thing over time, I'm sorry, which is an answer to Cheng's question. Okay, so Cheng's question was from last class was, what if you have a tensor product of two vectors? Okay, so the tensor product of vectors u and v. How would you visualize that? My answer now is I will first break it down into a symmetric part and an anti-symmetric part. Right? So going back, oh, okay. If any of you have to go, that's all right, because I'm going to keep talking for another couple minutes just to go back to my my iPad. Come on, there it goes. Okay. What if I have the tensor that Cheng was asking about? Tij is ui vj, like this. Well, I can break it first into symmetric and anti-symmetric. So the symmetric part, Sij, is ui vj plus uj vi over 2. The anti-symmetric part is ui vj minus uj vi over 2. So I want to visualize those things separately. Okay. For the anti-symmetric part, I'll transform that into a pseudo vector. So pk is 1/2. No, it's not. Yeah, it's 1/2 epsilon ijk ui vj minus uj vi. Right? So that is the same as epsilon ijk ui vj, right? Because this thing is anti-symmetric and this thing is also anti-symmetric. Right? And so this p vector is just the cross product, u cross v. You know all about visualizing that. Right. Okay. Then the S, this thing changes into an ellipsoid. It has 3 special directions and corresponding eigenvalues, this ellipsoid. Okay? I can't tell you in general what those directions are, but I can say one direction, one of the special directions is u cross v. And the other 2 directions are in the UV plane. This direction has an eigenvalue of 0. Okay, because if you take the product of this symmetric tensor contracted with a direction that's perpendicular to both u and v, you get 0. And the other 2 directions are non-zero eigenvalues. So this is what I can tell you about the answer to that question.
Okay.
It's not the greatest answer I could imagine. Maybe there's a better answer than that, but that's what I can tell you so far about that one.
Okay, thank you very much.
Okay. So sorry for that delayed answer and the delayed class in general for now, the overtime class. That's all I have to say for the moment. If any of you are still interested and still care, I'll answer any other questions. Otherwise, I'll see you guys on Friday.
I have a small question. Could you please go back to the page where you were talking about the reflection transformation
Yes.
of a pseudo vector?
This one?
Right, this one. I think that the pseudo vectors transform under mirror transformation differently from the proper vectors, not only in the sense that they change signs under the normal component. For a proper vector, the normal component of the mirror would change sign. For the proper vector, the component normal to the mirror would change sign, right, under the mirror reflection. But for the proper for the pseudo vector, I think the component in the mirror plane would change sign under this mirror transformation, right?
Let's think about that. Okay, so suppose the disk is spinning this way.
Right.
Okay, and over here it looks just the same. Okay, so if the disk is spinning this way, and it has an L like that, and here it looks just the same, so it still has an L. Like
right. Right.
Okay. So that the angular momentum is the same when you do this reflection operation, right? Whereas for a proper vector, the component perpendicular to the mirror plane would be changing sign under the reflection, right? And so, yeah, you could say that the pseudo vector does the opposite thing of a proper vector, right? Under a transformation like this, right? But what the opposite thing is depends on the direction relative to the mirror plane.